Dear students, you're welcome once again to this wonderful video of hydrodynamic chapter series. And let us quickly discuss the later part of the section of hydrodynamic, which I call the introduction to viscosity. About viscosity, I believe we might have studied that in our previous classes or in our early classes as usual. And we define viscosity as the intermolecular force. We can put down this in writing. The intermolecular force that acts between the layers, of fluids. And causes the intermolecular force that acts between the layers of the fluid and causes frictional force. A frictional force along the direction of flow. So basically what I'm trying to say here is that the force that acts, the intermolecular force that acts, or the frictional force that acts between the layers of fluid is called viscosity. It's very simple to define. It's not always necessary to cram. It is not part of my own way. I believe to understand stuff very well, you should be able to define your own way. So the only thing we want to know is that there are some intermolecular forces between the layers of fluid, which we've discussed about different types of fluid before. So this particular intermolecular forces will now act like frictional force on the layers of fluid. We should remember from early classes during our SS1 and SS2 days, we are taught about what is called frictional force. That is when you have what we call a block of mass M that is resting on a plane, as you can see, like this. I'm trying to bring out something. So if we consider block of mass of M like this resting on a plane, because of the weight of a body, which we call the weight of a body is always acting downward, that we have studied before. Weight of the body is mg, the block is having that of mass M. We have known that we have been told that if this is a rough surface in early classes, then there will be a force. If a force is acted upon in this direction, according to Isaac Newton's law of motion, there will be another force that is going to act in opposite direction, third law of motion. To every action, there is an equal and opposite reaction. This is the force acting upon this point, and the force which opposes the direction of motion of this, we say frictional force. Now, the same thing also happens in layers of fluids. If we have layers of fluids, as I've explained, can also take that into consideration. Now, if we try and do that directly, we can say the layers of fluid is having something like that, and on top of the layers of fluid, we have something like this. Now, you can ask me if you watch that in the downward layer, I use something like a straight line, but when I actually want to explain the one up at the uppermost part, I am using something like a streamline. Now, this is because we know that towards the particular point here, towards the downward part, the weight of the whole material, which I have explained under the first video part of hydrodynamics, we had. And because of that, the streamline here will be something like a short will be very, very what? Very, very small. I think the pattern of this will be in this form, as you can see. Then as you move up, the streamline will be what? We continue to what? Increase like this, as you can see. Trying to adjust that for better understanding. Now, what I'm trying to say is that the flow of liquids inside a particular medium is also affected by a particular force. That force we call viscous force. And that is what I'm trying to bring out here. From here, if we try to draw from what we have studied, we are considering a particular height let's say we are considering a particular height. We call that height of here. I'm considering the height here is a height of y. And we say this particular liquid is flowing with a particular, let's say with a particular speed we call v. So if I want to talk about as you move upward, you can see that there's an increase in the flow. And this is because of friction that reacts on top or below the surface here. So at those particular points, let's say we are moving from a point of V to a point of what we call here, it will be increased. The velocity of flow will increase here to V plus dV. I'm just trying to show illustration. I'm not asking students to have issues with what I'm trying to do now. Just trying to let you know that as you move up, the velocity of flow will increase. And this is because between the layers now, between the layers of flow that we are trying to show here, we are going to have a particular force that is moving in opposite direction, which I'm trying to show now. That is against what? Against the direction of velocity of flow of the liquid. That particular force we call what? The viscous force, which we denote by Fv. So students must always keep this at the back of their mind that this viscous force is as a result of intermolecular forces acting between the layers of what? Liquid. So here I can say the height from here, height of here from here to here is y. So if I move from here to the next point here, it will be what we call change in y. You can call that the y. All these are just to illustrate, to tell you that what, as you are moving up, the height is what is increasing, and as the height is increasing, what happens? The speed of flow is also increasing. Why? Because the intermolecular forces between what? Between the layer is reducing as we move from down towards up. And that is what we are saying. So the viscous force around, we move in opposite direction, and that is why we can also call it what? The frictional force that acts between layers of air. Now, we must also keep this at the back of our mind, which is also very, very important. That viscous force, we can take a note on that as well. A viscous force depends on some conditions. So which later in the part of the in the part of the slide, we are going to talk about the conditions in which this viscosity actually depends on. So for now, I just want us to understand, because we are doing introduction, just to understand that the intermolecular forces that causes friction between layers, between the flow of liquid, is called viscosity. And it is almost the same thing as what you have learned in your junior classes when you talk about frictional force that acts between the layers of solid. So always keep that at the back of your mind. And let's continue in the next sheet. Fine. Now, about the next sheet, what we have here in the next slide is to discuss some important points about viscosity. As we have already discussed in the previous slide, that viscosity depends. We said that viscosity depends on viscous force. We can just write it in front. The process is viscosity. The force acting is called the viscous force. Now we can write that viscosity, let's just write viscosity, we can take down a note, depends on the intermolecular forces of fluids. Very important for students to keep this in mind. And when you say it depends on intermolecular forces of fluids, what we are saying indirectly is that it depends on the what? On the nature. You can also write it because of a MCQ, multiple choice question. We say it depends on the nature of what? Of the fluid. You can see that is why some of your teacher will tell you that viscosity is more or less like opposite of friction. As friction do not depend on nature of surface, but viscosity depends on the nature of surface or the nature of the fluid. That is the intermolecular forces between that. Another point we can put down on viscosity, which we can also take on, which is impossible, it's also possible, is this. Now, to understand this, there's what we call the coefficient of viscosity, which I have not talked about. like I said, the viscous force depends on some certain parameters, which I can quickly break down. For you guys to understand the concept of viscosity very well, you need to watch the video series with respect to the way it is being arranged on the page. Now, viscous force, we say is the force or frictional force that acts between fluids. Then it depends on some certain factor. One of the overall factor of viscosity of viscous force is the intermolecular force. The intermolecular force depends on some other factors, which we say viscous force also depends on. So what I'm trying to say now is that the measure of intermolecular forces between the layers of liquid or fluids, as the case may be, depends on what we call the coefficient of viscosity. It may look hard to understand the concept now, but as we progress in the topic, I believe very well that we are going to get it. Now, what I'm trying to say is that intermolecular forces that we're talking about is called the coefficient of viscosity. Now, talking about viscous force, we said it depends, because we are going to have a slide according to the duration of the slide that we are going to discuss on some certain factors that affect viscosity. And that is why now we want to write some facts which we need to put down, which we are still going to meet in the later slide as we move in the topic of viscosity. So by and large, my point is what when we talk about intermolecular forces, we are talking about the measure of what? The coefficient of viscosity. So we need to keep this down also about some facts about viscosity, that the coefficient, you can write coefficient of viscosity in liquids is greater than that of solids, of gases. We are considering fluid as no solid, of gases. So we can say the coefficient of viscosity we denote by a symbol we call eta. Eta is written like this. So eta of liquid is very, very greater than that of eta of what? Of gases. In fact, in real gases, that's why I say you have to follow the trend of the video. In real gases, that is when we can have what we call coefficient of viscosity or intermolecular force. We assume in an ideal gas that there is no what intermolecular forces between the layers of gases. Do you understand? So that is why we said the measure of intermolecular forces, which we call the measure of viscosity coefficient, is not present in gases. But when we consider real gases and not an ideal gas, you know, in the topic of hydrodynamics introduction, we discussed about real and ideal gas. And I told you categorically that we are going to, in this slide or in the topic as a whole, in general, we are only going to be talking about what an ideal gas and what we are going to declare the real gases. Because it is very, very difficult for us to have a real gas. So we'll just take an ideal gas that will follow some of the parameters I have mentioned in that video. So by and large, my dear students, we are to keep it in mind that coefficient of viscosity in liquids is greater than the coefficient of viscosity in gases. Another important point we can also put down, which I think is important, is that let's talk about the density, which is also very, very important. We can say the density is called DEN. Density increases the viscosity of liquids and decreases the viscosity of gases. This is another important point we also need to understand the concept of viscosity very well. As we might have also studied before, that when you consider taking pouring, let's say, water Let's say, for example, water and oil. You guys know very well that what there will be a free flow. When you pour water on a level ground, water will flow freely compared to the way oil is going to flow. We don't need to cram. We need to understand this. You can visualize what I'm trying to say. So my point here is that the reason is because as density increases in liquids, the viscosity also what increases. So that is that. Whereas as density increases what? As density increases in what? In gases, the viscosity tends to what? Increase. Density of oil is what? Thicker than that of what? That of water. The same thing you can compare on. These are early classes or illustrations I believe we might have what heard before. So water comes out from a free container from a container than what the way only will come out. What is the fact? Viscosity. Because density varies directly with what viscosity for liquids. But in the case of gas, why? Is because I told you, in fact, we say from our kinetic theory of gas, if you still remember, what happened? The more they try to come together, what happened? Gases are what are spacious. They have space. Yes or yes? They have space. Because of the space between them, that is why they what we say they don't have what intermolecular forces. And we are talking about intermolecular forces when we are talking about viscosity. I hope you understand the relationship. Another thing we can also put in down for some important facts about viscosity is that the coefficient of viscosity we discussed about, the coefficient of viscosity, we can write the coefficient of viscosity is measured in Poiseuille. That is what we call it, Poiseuille. So be careful about Poiseuille, which we denote as PL. That is the SI unit of coefficient of viscosity. Remember I told you the coefficient of viscosity is denoted by this, which is called eta. So this SI unit of coefficient of viscosity is Poiseuille. But when we talk about the CGS, because of conversion, in most of our numerical, it should be given in CGS. So you should always note that one Poiseuille is equals to the CGS. Let me just write the CGS unit. CGS, the CGS unit of coefficient of viscosity is written as poise. So be careful about this because when we start some illustration and we are going to be doing conversion, the standard unit of coefficient of viscosity should be in what? Poiseuille. Later in the part of this topic, we are still going to talk about the Poiseuille equation. Now, for now, let us note that what the SI unit of coefficient of viscosity is Poiseuille, and the CDS unit is poise. Well, keep it in mind that one Poiseuille, that is one Poiseuille, 1 PL, is equals to 10 poise. Just like the way you convert 100 centimeter is equals to what? 1 meter. For here, one Poiseuille. That means if the SI unit, if the unit is given in CDS unit, which is in poise, you convert it back to what? To what? Poiseuille. And Poiseuille is denoted by PL. And this is what we need to keep in mind about some parts of viscosity. Let's quickly move to the next slide in continuation of what we have. But fine. The next slide is talking about the factors that affect viscosity. Now, like I said, that we are having a slide that explains some factors that affect viscosity. And I've explained that talking about the frictional force that acts between the layers of what? Of fluids. It's called viscosity. Looking at that, I said the major factor that affects that is because of what? Intermolecular forces acting between the layers. And hence, students need to keep this at the back of their mind that when we talk about intermolecular forces, we talk about viscosity. We say viscosity is affected mainly by the following factor. The first factor we can put that, I can quickly draw and explain this, but because I've done that in the introduction, I don't want to waste that time because we still have a long way to go. Now, about factors affecting viscosity, we can say viscous force, let's put that in a note. Viscous force is affected by the following factors. And the first factor we can put in mind is what? Viscosity is affected by what we call, I said it depends on intermolecular forces. That means also depends on the what? Area. Area of surface of fluid, or area of fluid. The area of what? At which the fluid are flowing. Another factor we can keep in mind is that viscosity also depends on another important factor we call what we call velocity gradient. Very important for students to understand that from my illustration and the first part, I said the rate of change of velocity with respect to the height. I consider a height of velocity of v in which the fluid is flowing, and I take a height of what? Of y. So it can be the v by the y. In some of your test material in your examination, the examiner can put it as the v by the x. So always keep that at the back of your mind that velocity gradient is denoted by rate of change of speed with respect to the distance it's covered. So here I'm taking the v by the y. So it can be the v by the s. It doesn't change anything. So indirectly, we can say, we can express this mathematically by saying that viscous force of viscosity, which are called Fv, is directly proportional to what we call, please be careful when you are dealing with all these things, to area. That is one. The viscous force is directly proportional to velocity gradient you call the v by the y, according to what I have here. So directly mathematically, we can conclude that viscous force, when we combine these two together, is now directly proportional to A multiplied by the v by the y. So this is the way we relate that. And there will be a constant of proportionality when we set variation sign to equality sign. And directly we can say viscous force Fv is now equals to eta, which is coefficient of viscosity, A dv by dy. So students need to keep this formula in mind, because in lots of questions and theoretical questions, illustrations, and numericals, we are going to be using this formula to solve some questions. So again, you can also put in mind where n here is called coefficient of viscosity, which we said is measuring what? Horizontally. I hope you still remember viscosity. So this is that about that, dear students. And you can also keep at the back of your mind that this coefficient of viscosity depends only on what we call intermolecular forces. So that is that about the factors affecting an area, velocity gradient, and what intermolecular forces, which is more or less the same as the coefficient of viscosity. Next, we move to the next slide in continuation to this. About the next slide, we have Stokes' law and terminal velocity. So in sequence to this, in the syllabus, we are to discuss a very, very important law that is derived from experiment, which we call the Stokes' law. Now, about the Stokes' law, we need to understand how we come about that, and let's put on a note to understand the concept very well. About Stokes' law, we can write that if a sphere, we can just write if a sphere, which is a solid, anyhow you want to write it, is dropped. If a sphere is dropped into a fluid, and it is in contact, with the fluid. We are talking about, we are dropping a solid into what? Into a fluid. And what? The layers of the solid, of the fluids, are in contact with the fluid, comma. I'll just take that, comma. So we can say there will be, for understanding's sake, there will be a viscous force, viscous force due to the contact, between the solids and the fluids. So we keep this at the back of our mind, like I said. We've talked about this. So, like I said, we are still here. Now, there'll be a contact between the fluid. When you drop a solid into a fluid that is in motion, there'll be a contact between some layers of the fluid will settle themselves around that of the solid. And because of that, viscous force will be generated between the layers of the fluid. So this, as the velocity or the speed, we talk about the speed of fluid, as they tends to increase, what you see is also the viscous force that is generated between the layers we also increase. We can understand this one very well by actually trying to bring some illustration for better understanding and classification of this concept. So we can just do that at some parts here, and let's quickly show how that works. So let's consider a fluid layer according to what you can see. A fluid layer like this, for better understanding of the concept and understanding of how to solve questions. So let's say we have a fluid layer that is motion of fluids. Now we are going to drop a sphere in between the layers of the fluids. So let's say this is a sphere that is dropped. Okay, fine. We have a metallic sphere is dropped inside the layer of the fluid. As you can see, diagram we're going to scale. Now, because of this, there will be something like a contact between the layers of the fluid. Now, this sphere is having a velocity directly. For understanding's sake, we've talked about this before. This is having the velocity of, let's say the velocity of this flow of this fluid is moving with the velocity of v, as you can see. So there will be some contact between this layer, as you can see, so we have, there will be some contact between the layer of the fluid, excuse me, guys. So let's say there will be a contact, something like this, between the layers of the fluid, and that this will be in contact with this. And because of that, they will also generate a viscous force, which we have discussed in opposite direction. What you understand is that as the velocity of flow of the fluid is increasing, what happens is the viscous force also tends to increase. So this is the theory behind the experiment of Stokes' law. So for now, at the point of contact, there will be a relative motion between the speed. The speed tends to move as the speed increases, the viscosity or the viscous force will also tends to increase. So now, according to Stokes, we can now write to understand the concept. In continuation, we can write that according to Stokes' law, according to Stokes' law, considering a sphere of radius r, and velocity and speed. You can write speed or velocity anyhow, please, and speed v. The viscous force VF will be given as, or viscous force VF is given as, we have viscous force between the layer is given as 6 pi eta RV. Now, right now, my dear students, I'm not going to be going for the derivation of this formula because it is mainly on an experiment. So now, according to Stokes' law, the viscous force acting between the layer of what, of a solid that is dropped inside a fluid that is flowing is given by 6 pi eta RV. The only parameter, the student should be careful about this. This is viscous force, you understand, and this is the velocity. The V here is velocity. So if you write viscous force of F, please be careful, it's viscous force. Eta is what? Coefficient of viscosity. Every parameter here are constant, only the radius and the velocity of flow. So please keep that at the back of your mind. This particular value will be given in calculation, and you know the value of pi to be 3.14222/7. So be careful about this. And this is what we call the viscous force that acts between the layers of fluid according to Stokes. And this formula is the formula we call the Stokes law. So keep that at the back of your mind. It's very important because we are going to be in need of that as we move forward also in this topic. So in continuation to that, we are also to talk here about the terminal velocity. About the terminal velocity in this slide, we are still going to talk about it as we have studied. Now, in continuation to this, as we have studied that as the velocity of the material, as the velocity of the sphere, I'm considering a sphere, which was what was used in the experiment, as the velocity of the material or the sphere continue to increase, what happened to the viscous force? That also stands will continue to increase. There will be a particular time, as body is gaining velocity, with time the body will start accelerating. So there will be a particular time whereby equilibrium will be set. When I say equilibrium, the body will stop accelerating, because when it continues to flow and the viscous force is continuing, so there will be a time where they will balance out each other. So this particular point at which the body is no more accelerating, this point we term the terminal velocity, which students need to keep in mind. So we can put down something in writing for understanding's sake. We can say that in continuation, we can write as we might have here, we can say as the point, you can say as the viscous force increases, as the viscous force increases, we have the velocity increases to a certain point, where equilibrium is set. To a certain point where equilibrium is set. At this point, the body, that is the solid body, is not accelerating. It's not, or it's no more, I think that is better, it's no more accelerating. So this point at which the body is no more accelerating, we say acceleration of the body is 0. The point at which the body is no more accelerating, whereby the acceleration of the body is 0. I said at this point, the body is it will reach at a particular point. At this point, the body is no more accelerating, and this point is called the terminal terminal velocity. So for definition and interpretation, I have tried to make it a little bit longer. But if you want to write what is terminal velocity, I can just directly write as what the point at which what the acceleration of a metallic sphere or a body that is dropped into a fluid is equals to 0. At that point in time, we say the body has reached its terminal velocity. At that point in time, the body will not increase, but now it will now maintain a steady flow. In our junior classes, we might have studied that something like when we try to plot a graph of terminal velocity, it will start to increase first when the body is accelerating. But when the body stops accelerating, the body will now maintain a straight line. This straight line point is what we call the point of what terminal velocity in junior classes. So which is also the concept we are trying to explain here as well, or we want to lay on that particular concept. So to explain this thing, because we need to know the velocity formula at terminal velocity, and doing so, we are going to use the same sphere here and to explain the concept. We have talked about body is accelerating, and at a point, the body will have the acceleration that is equals to 0. And at that point, the velocity of flow here will turn towards terminal velocity, which I call VT. Everybody knows because of acceleration of the body, which is acting towards this direction, along the direction of flow, we can say that the weight of this body will always act downward. Everybody knows weight is mg. And because of this, there are two things that is happening here. We need to understand. I need to finish up quickly because of time. I'm being signaled to rush up, and I don't like rushing because I want you guys to get all these clear concepts. Now, here we say the body is having the weight of this body dropped here, is acting in this downward direction. The body has stopped accelerating. And at that point, we said it has reached terminal velocity. And because it has reached its terminal velocity, we have upward force that is acting here. There are two forces. The viscous force is acting upward that we have just discussed, told you between the layers. So we are considering the layer here, the viscous force is here. And again, there's another force that is acting on top of the what? When a solid is dropped inside the liquid, static friction, static fluid. We talk about buoyant force. So there are two forces acting here. The one that is acting on top of the solid that is dropped, and the viscosity force that is also acting. So due to equilibrium that I said, there will be a time at which for terminal velocity, what you can just bring out now is that the viscous force plus the buoyant force will balance out the weight, which is equals to mg. So directly, my dear student, we can conclude here that the viscous force, according to Stokes' law, we've done that FV or VF. Anyhow you are writing it, it should be FV. I'm writing VF. Let's write this as FV. It should be better, so that you will not be taking viscous force as what velocity. So the viscous force here from formula we have here is 6 pi, because we are using the viscous force is we have 6 pi eta RV. We just need to listen to this point. Plus, remember, buoyant force, we've done that before, is V rho G. I hope students to remember that is equals to the mass here is mg. Now I'll quickly do some conversion here, which I will show you. Remember, let's consider two other things which is important. We take the density of the liquid to be what? Rho L, and density of the solid to be rho S. So let's just convert. We know that density is always equals to mass over volume. So let's keep that at the back of our mind. And here we are talking about 6 pi eta RV from here plus, look at this, this is volume submerged. You guys know that this is 6 pi eta RV. We are adding that plus volume submerged. We are talking about volume. So volume is equals to, from here, you can make volume to a formula. Volume is equals to mass over density. You can also do that. Volume is this mass over density. So here I can take that as volume here is mass over density, or if you don't want to do it like that, you can leave the volume here as volume, then change the density here to be mass over volume. So anyhow you want to do it is always good. So just have it at the back of your mind that the volume submerged, you know, what we submerge here is volume, and the volume of a sphere, because I will work with respect to that for understanding's sake. Remember from your mensuration classes It's looking very rough, but we can still get it. Volume of a sphere is 4/3 pi r cube. So please keep that at the back of your mind. So I can just substitute this here. I have 4/3 pi r cube. Then density here is mass per unit volume. I can multiply that by density is mass over remember, we are talking about the volume sub mass. So the volume here is also, so I would love to have actually work with respect to cancel. This is not volume. Please, we need to understand that. This is not volume. So we are talking about this one, and we're taking this one to be the terminal velocity. Or basically, we can say, well, we can still write this one as rho or m, anyhow you want to write it. But let's leave it as rho. This is rho of, for understanding's sake, I'll take it as rho here, rho of solid, rho of liquid. Sorry about that. Rho of liquid is equals to, now here I will change. We're talking about the whole weight of the solid that is coming down. So mass is equals to density times volume. So directly here I can say this is now rho of solid, because we're talking about weight of the solid, multiplied by volume of the solid, then multiply by, you can see, volume of the solid, we have volume of the solid multiplied by G. So this is what I'm just trying to bring out. So we can also substitute this value because it's very important for us to get all these parameters. I've changed this one to density, mass equals to density times volume. So if I go by that, by cutting without wasting time, because we only need to know this one now. Here, I'm taking this one as the terminal velocity here, because the velocity has changed to Vt. Please be careful here. When I try to cut whatever I want to cut, you can try the mathematical aspect here. And when you make Vt sort of formula, we are going to have what? The terminal velocity according to that one. What I did is I balanced out this with respect to this. And I use Fv, the viscous force, is 6 pi eta Rv. So, and I'm using the volume of sphere to be 4/3 pi r cube. So please keep that at the back of your mind. I substitute. We also change this one to 4/3 pi r cube. You cancel what you want to cancel. Then substituting that, what you are going to have is this will give us from numerical, the formula you have to keep in mind will be 2/9. Yeah, that is 2/9. Very good. Here one, here two, I have 2/9. I have r square. We open brackets. We have rho of solid minus rho of liquid divided by eta multiplied by t. So please keep this formula in mind, because this formula is very, very important when we are calculating terminal velocity. The formula for terminal velocity, when a sphere is dropped and it has stopped accelerating, from calculation, from what I've shown on how to get the formula is given by formula directly. You can put it at the back of your mind. You can finish up this as an activity because of the space here. That is why I have to stop. But from what I have here, you can cut, take LCM, cut what you can cut, change this one to 4/3 pi r cube to cancel out, and you are going to see you have to be 2/9 r square, because this will get cancelled out, remain r square here. Then we have rho of solid. This one will move to the LHS, to the RHS, minus rho of liquid divided by, where is eta? You can see eta here. Then pi will also get cancelled out. When you cancel, then you have multiplied by. So this is the formula we apply directly to solve questions on terminal velocity, which you also need to keep in mind for this your exam. A-level physics. So next one, we move to the next slide. In continuation to what we have. Oh, fine. Now the next one is a Poiseuille equation. About Poiseuille equation, now I think we can now understand the concept between what that is we have been talking about since morning, and that is the concept of viscosity. Now about viscosity, we said the coefficient of viscosity is measured in Poiseuille. Now Poiseuille is having a particular equation which we can also consider very quickly. And to do that, because of time, like I said, I have to up my pace. Now, because of time, directly we can say, according to Poselli equation, we can take I just want something so going to make sense. So let's just consider this, as we might have discussed before in hydrodynamics, which is what the first video before this. Now, about this, we said we consider a pipeline or a tube or whatever you want to call it. You are free to call it anything you feel you want to call it. Now, considering this, now we can quickly, okay, fine. Now, let's look at this. Now, we said that we have a tube of length L. The length between the tube here is length L. It's having a radius. You can say it's having a radius. Radius of R. I'm going to show radius. I hope my students know radius very well. This is radius of R, as you can see. And we can say maybe we have a flow of liquid flowing through it. Diagram not going to scale up, just for understanding's sake and because of time. So we have liquid flowing from one point to another. We have definitely we know there will be a speed. We can call this one at this end as VA. We can call this one as VB, anyhow you want to call it. Then we know that if it is not a what? If it is not, we are considering a real fluid. If it's an ideal fluid, there is no coefficient of viscosity, or there is no viscosity between the layers of the fluid. But here we are considering what we call a real fluid. So considering a real fluid, can also put into consideration that what we have here, let's say the pressure at this point is rho pressure is PA, and the pressure at the point here I can call what PB. So according to Poselli equation, which was also derived experimentally, from Poselli equation, we can say. Now, what he said was that we have talked about continuity equation and stuff like this in our previous video, but now we only want to talk about experiment of somebody in the laboratory. So the formula was given directly. Considering this, it's having a coefficient of viscosity between its layer. We are going to take coefficient of viscosity as eta. We know that because it is what a real fluid. Friction, what I said, friction will set up between the layers of this liquid. And the friction is what we say, we take that as coefficient of viscosity. So we know that volume equals to area times what? Times radius. And here we are considering the circular part. And if you consider the circular part, you can say the circular area of a circle is equals to, everybody knows that, pi r squared. So now directly from this experiment, looking at this, we can now say according to Poselli equation, you just need to understand the velocity of flow per second with respect to time is given according to Poselli equation as, you can keep this formula at the back of your mind, which is very important because it's what derived experimentally. So Poselli equation gave us the formula directly that we have pi r to the power of 4 divided by 8 eta L. Then we have multiplied by change in pressure. So which change in pressure can be PA minus PB or PB minus, if it's flowing from here to here, it will be PB minus PA. And if it is flowing, so we talk about the flow velocity per second. Velocity of flow per second is given directly by this formula. And this particular formula is called the Poiseuille. You can see the spelling of Poiseuille itself, equation. So please keep that at the back of your mind. And this is the way we relate the Poiseuille equation for the sake of what numericals. And sometimes we can come about questions we can never say. So when you see question that ask about Poiseuille equation, this is that. And remember, I told you about coefficient. One Poiseuille is equals to 10 points. Always keep that at the back of your mind. Don't forget to convert. And that will be the end of our video section for this. The next is the illustration, as always, which is one of my favorites, because after we've explained concepts, we only try to do one or two illustrations You can always try more illustration from your test materials, and this is always going to tell you where you work, if you understand it or you still need some help. And if you need help, you can always send what the questions or the area you need help from. So about that, let's quickly look about some illustration and quickly solve the illustration we have. Fine. About this, in this slide, I think according to the boys that prepare it, we have two illustrations to solve also, because this is the end of the slide I have here. So here we have two illustrations which we can see directly. We have the first one says we are to calculate the terminal velocity of a brass ball 1 millimeter in diameter falling in a tank of glycerin. If the density of brass and glycerin are 8 grams per centimeter cube and 1.32 grams per centimeter cube respectively, and we are to take the viscosity of glycerin to be 8.3 poise. I told you viscosity should be measured in what? Coefficient of viscosity should be measured in what? Poisillic, not poise. And G is taken to be 10 meters per second square. A lot of things needs to be changed here because the answer is in centimeter per second, as we are talking about the amount in terms of per second. Now, directly we can just say, according to terminal velocity we have actually derived in the concept video, we can write or we can solve and say solution to this can directly be written as we have the velocity of terminal velocity. Remember the formula, you have to keep it in mind. Is given from derivation as 2 by 9 r squared. We open a bracket. We have a rho of solid minus rho of liquid. We close off the bracket. We divide it by coefficient of viscosity. Then we multiply everything by G. So this is the formula we are going to use to solve this question. And we are going to do that together by, first of all, bringing out the parameters and doing the conversion as integral. So directly, what we need to do here is just to get our calculator very close to us and do some conversion. Now, directly, we have diameter was given instead of radius. You can see what I'm saying? We have to get radius. Radius is half of diameter. Everybody should know that. So we divide 1 by 2, and that is 0.5 millimeter. I'll convert this to centimeter. And I know 10 millimeter make 1 what? Centimeter. So I can just do that by saying if you have 10 millimeter is equals to 1 centimeter because of time. I'm sorry about that. So that means if I convert that, I will just divide this one by 10, and that will give me 0.05. So we divide 0.5 by 10. Please don't let us make mistake because we are rushing, doesn't make us not to solve well. So divided by this is 0.05 centimeter. I hope students understand this, and I hope I can move on. Now the next point is it's having a density of brass. Brass is the solid. It was brass that was dropped. So we need to get that. This calculator, I'm having a calculator here. So brass was dropped, and because brass was dropped, we know that the rho of brass, that's rho of solid, is what? It's given in 8 grams per centimeter cube. That is why I'm working in centimeter. And what? Glycerin is the liquid. So the rho of the liquid, density of the liquid is 1.32 grams per centimeter. So the rest is coefficient of viscosity coefficient is given as 8.3 points. I know that 1 Poisillic is equals to 10 points. So if I'm converting from points to Poisillic, I have to divide by 10. I hope students understand this. So doing that, I have to 8.3 points. So 8.3 points. I'm not supposed to be showing all this, but because when I give us x, you can just say divide 8.3 divided by 10 is 0.83. So I've converted coefficient to 0.83. What's that? The SI unit is in Poisillic and not in points. So that is 0.83 Poisillic, which is what? PL. The next thing I do is just to distribute the parameter and get the answer. You can say velocity of terminal directly can be 2 by 9. We are taking the square of 0.05 square. Let's do that directly. 0.05 all square is giving us 0.0025. We are subtracting these two values. I will do that directly. We are subtracting 8 minus 1.32. We are dividing the value here by 8.3. Then we are multiplying by 10. So directly, let's do something, guys. We multiply this. I'm doing this side 0.0025. I'm multiplying that by 2. I'm dividing the value by 9. Please, you can go to your calculator. What I have here from my calculator is 5.55 repeating. That is why I'm putting the 8. I'm multiplying that by 10 to the power of -4. Then I will multiply all the answer by, look at this, guys. I will subtract 8.1, 8.8 minus 1.32, which we need to do. That is giving me 6.68. I'm dividing that by 8.3 directly from calculator. By 8.3. I'm having here, I'm having the 0. This is 5.55 repeating times 10 raised to power -4. I'm multiplying that by, the answer I have here is 0.8048. And we multiply that by 10. So doing that with calculator, we should have multiply by 5.55 times 10 to the power 4 should be 5.555 times 10 to the power 4 should be 0.0001. It's giving me something like 4.47 times 10 to the power 4. So if I multiply that one by, so I'm having something like 0.47. That's what I'm having here, not 0.77. So let's do that again to avoid mistake. I multiply this by 10. I'm having 0.040047. So which is none of the option here. That means calculator error, we can always check. And that is what I want to run for. 8 minus 1.32. Already will give us 6.68. We are dividing that by anyhow I'm doing this, this should be 6.68 times 0.0025 times 2. We have 0.0334. So now that's what we have at the numerator. Then the look at this, guys. I have G is 10 meters per second squared. And that should not even affect my question to my answer to. So if I want to convert this one to centimeter per second, I have 10 meters per second squared over 1 second squared. I want to convert to centimeter per 1 second squared. So I only convert, you can see 10 meter, we know 100 centimeter is equals to 1 meter. So if I'm converting from meter to centimeter, I have to divide by 100. So we have to understand that. So if I divide this one by 100, I should have centimeter. So I'm dividing 10 divided by 100, and I have centimeter per second squared. So if I divide that by 100, it will change a lot of things. So I can say here 1 by 10, which is 0.1. I can say, okay, fine. I think it's okay like this. So let's do something. Every answer here is still multiplied by 0.1, which will make this one to be 10 raised to the power -5. It's still the same thing. So answer here should be 6.68 times, I think there's a typo there, times 6.68, not times. We are dividing by 8.3. Then I am multiplying the answer by 5.55 times 10 raised to power. That will change to -5. This, you can always do it with in your own way. And what I'm having here is still, what I have is still 4.44, 4.46, that is 4.5 times 10 raised to power -5. So please note that. That is what I have here, and that is what is in centimeter per second. So that should be the answer to the question. We're not going to waste time. You can verify with your calculator. I might actually make mistake, which is very, very rare in my calculation. You can confirm that about this. 2/9 r squared, you open a bracket, rho of solid minus rho of liquid, divided by eta. And if you divide that by eta, then you have this is 0.83, but it's still going to change. This is 0.83, you can see. So those are simple, but it doesn't change a lot. I'm not sure it's going to change a lot. It will only reduce that thing by 1. So the answer should be around 4.4 or 4.5, but we don't have anything in terms of that. So let's do the last question here. This is valid. And the last one is we have with what velocity is a steel ball of radius r and density rho falling in a tank of glycerin, glycerin again, of density at an instant when the acceleration is 1/2 that of the free falling stuff. So we don't need to waste our time. We have studied Stokes' law and we have studied the formula that the terminal velocity at that point will be 2/9 r squared. We open a bracket, rho of solid minus rho of liquid divided by eta multiplied by g. The only condition that is changing here is that the acceleration is 1/2. 1/2 means half. Please note that. So if g is equals to 1/2, 1/2 is written as 1/2. What do you have, guys? The formula will only change to Vt equals to 2/9 r squared. Then we open a bracket, rho of solid minus, sorry about that, rho of liquid. We are dividing that by eta, but g now is 1/2. Everybody knows what happened. 2 gets cancelled out. As you can see, 2 we cancel out that. Directly we can say, therefore, for our answer, the velocity of terminal velocity is equals to, that is 1/9. We can write it as r squared by g, open brackets, r squared by 9, not by g, please. Rho of solid minus rho of liquid divided by eta. So you look at for option that look like this, and that is what is the right answer to the question. So guys, I'll be stopping here. I think the correct answer to this should be r squared by 9, r squared by, okay, we have r squared, okay, 1/2g, please. That is also important. That is why numerical is also good. This is g is 1/2g, so g will still be there. It's only that g is now half of the other one. So we have g must be here. So you can see r squared g, this is wrong. Option A is wrong, so we have to check this. You have r squared g. You can see this one that has 2 and has 2 is also wrong. So the correct answer is option B. Please keep that at the back of your mind. You have r squared g, and look at r squared over 9. Look at r squared times g. They give you r squared g over 9. Open bracket, rho of solid minus rho of liquid divided by, you can see, look at this, 9 times eta is what? 9 eta. Open bracket, rho of solid minus rho of liquid. So which is the same thing as what we've done. So I will stop here, guys. See you soon in the next video where we talk about the last part of this hydrodynamics, talk about capillarity action, surface tension, adhesive cohesive force, and load contact. And that will be everything you need to know about this aspect of what the syllabus. See you soon. Don't forget to subscribe to the channel. Thank you and